This document is linked to the vectors topic of the IB Maths higher level course. It's allowing students to explore the properties behind vectors with different properties on different pages. For example, on this first page you can grab either end of each vector, and as you do so the information on the left is updated for the components and for its magnitude. You can cross them over and do anything you want with either vector p or vector q. The next page is an opportunity. If you set this for students to work on at home, they could play around with the previous page and then record what they discovered on page 2.2, and this can be collected in using the Inspire Navigator software. Anyway, going on to page 3.1, we have a similar setup here, and this helps accentuate that vectors are not location dependent, because when I move this vector around its components don't change, but this time you can edit the components directly, double click on the 4, change it to a 6, and the vector is updated accordingly. Again, the feedback page is there. On page 4.1, we've got to make these tip to tail, and so if I put them tail to tail, nothing happens, but if I put them tip to tail, we can see the effect of the addition of vectors. There it is vector b plus a, and there it is the vector of a plus b. So depending on the order in which you connect them up, you can get equivalent vectors for their resultant force. On page 4.3, what you can do is move the whole diagram around and change the components of vector b. Let's just change the first component from a 1 to a 2, and the diagram updates accordingly. And maybe students can start to conjecture what the components of vector c are from already seeing the components of vectors a and b. On page 5.1, this just shows that if you have 5 vectors, or any other number of vectors, in a closed loop, then it does not matter the order in which you join these vectors together. And in fact, you can, just as long as you put them tip to tail, you can construct a very different appearing diagram, but which still has a net resultant of 0. So a chance to just play around with different configurations of vectors, which when combined have the same property. On page 6.1, we're starting to look at the scalar product, and here as you move vectors around, you can see that the scalar product, or the dot product, can go positive, negative, and indeed there might be a 0 lurking in there if we can get these vectors perpendicular, which isn't something which is easily able to be done there. But also the vectors don't have to be crossing over in order to be able to work out the scalar product. On page 7.1, we have the same configuration but with a little bit more feedback. When the scalar product is 0, it highlights it with a message that turns up, and likewise when it's negative. And so we can start to look to see if it's a acute angle or an obtuse angle between the two vectors. Again, the vectors don't have to be touching for this, they can be anywhere in space for the same messages to come out. On page 8.1, if we make them tail to tail, this basically showing that you can work out the angle between two vectors, but only when they're configured tail to tail. If you put them tip to tail, nothing is registered. And again, you can see the scalar product on show. And finally, on page 9.1, if you're having to look at splitting a ratio in any particular, splitting a vector in any particular ratio, you can move the vector point p either internally or externally, and you can see different ways of recording the information, looking at ratio of a to p and p to b, or a to p and a to b. So again, an opportunity for students just to conjecture whether they think the point p is closer to a or closer to b. Anyway, that's all it does.